Hey, we've already learned what we need to know about trigonometric substitution, but now we need to practice some problems, so let's practice some problems. And before we jump right in, I'll remind you of the basic idea. If you have something of the form a squared minus x squared in your integral, then let x be a times the sine of theta. If you have something of the form a squared plus x squared in your integral, then let x equal a times the tangent of theta. And if you have something of the form x squared minus a squared, let x equal a times the secant of theta. And in all these cases, you'll end up with some trig identity that turns out to be a perfect square and will let you simplify and integrate. Okay, let's take a look at this one. The integral of the square root of 4 minus x squared all over x squared with respect to x. And when I say let's take a look at it, I mean let's you take a look at it. Give this a try. So it's of the form a squared minus x squared, where the a squared is 4, so the a is 2. And so you would start. Never mind, you figure out how to start. So give this a shot. Get it down. You know, there are 3 parts to a trig substitution problem. There's the doing the trig substitution and coming up with a new integral. You should be able to finish that. Then there's the integrating that. You might get stuck there, in which case, we'll pause in between each step. And then there's this third part of turning your thetas back into x's, and we'll do each part separately. So what I'm saying is, I'm going to shut up now. You're going to pause the video and get as far as you can. And then when you get stuck, start the video up again, and we'll catch up together. Okay, you should have started by letting x equal 2 times the sine of theta, in which case dx is 2 times the cosine of theta d theta. This is what lets us rewrite the original integral in terms of the new variable theta. Everywhere you see an x, you write 2 sine theta. Where you see a dx, you write 2 cosine theta d theta. That gives you this expression here. And all I've done in this step is factor a 4 out underneath the radical and bring the 2 cosine theta up into the numerator. And the beauty there is that 1 minus sine squared theta is cosine squared theta, a perfect square. I certainly could have done some cancellation with the constants, but I'm in no rush because it's going to get even better in a moment. I'm going to take the square root of 4 cosine squared theta to simplify this. And the square root of 4 cosine squared theta is, of course, 2 times the cosine of theta. And so I have 2 times the cosine of theta times 2 times the cosine of theta, which is 4 cosine squared theta. And after you cancel the 4's and rewrite this more simply, we end up with the integral of the cotangent squared theta d theta. So we've just finished the first of the 3 parts of the trig substitution. The trigonometric substitution part, I guess you would call it. So we've gotten this down into a new integral entirely in terms of the new variable theta. And now you're saying to yourself, okay, how do I integrate cotangent squared theta? And if you haven't gotten this far before, then take a moment and think about how you would do it. Or if this was where you were stuck, then just listen on. But if you'd like a moment to think about it, then pause the video and we'll do it together from here in just a moment. If you recall, when we were talking about integrating powers of secant and tangent, I warned you that it was the same as integrating powers of cosecant and cotangent, and that those would come up later, and that later is now. So for example, if this had said the integral of tangent squared theta, well, that's one that we've seen before. We rewrote it in terms of a trig identity, and it became very simple. And if you start with the famous trig identity sine squared theta plus cosine squared theta equals 1, and you want to rewrite that in terms of something that has a cotangent squared in it, well, the cotangent is the cosine divided by the sine, so divide both sides by sine squared theta, and you get the trig identity 1 plus the cotangent squared theta is equal to cosecant squared theta, or cotangent squared theta is cosecant squared theta minus 1. And that gives us that our integral is equal to the integral of the cosecant squared theta minus 1 d theta. And you say to yourself, how do I do that? Well, if it had said integral of secant squared theta minus 1, you'd be able to do it because you remember that the derivative of the tangent is the secant squared. Same idea, derivative of the cotangent is the negative cosecant squared. And so when you integrate here, you just get the negative cotangent of theta minus theta plus a constant. And now we've done the second part of this three-part problem. We have integrated the expression that we came up with that was in terms of theta. All that's left is to now come up with an answer that's in terms of x. We start with the idea that x is equal to 2 times the sine of theta. So x over 2 is the sine of theta. And that tells us immediately that theta is the arc sine of x over 2, which gets us this part of the integral that we needed to figure out. But we still need to figure out what the cotangent of theta is. For that, we draw a right triangle. We know that the sine of theta is x over 2, so opposite over hypotenuse is x over 2. So we can label this side x and this side 2. And then this side is the unknown side that we can call a. And by the Pythagorean theorem, a squared plus x squared is equal to 2 squared. And after you do a little bit of algebra, you get that a is equal to the square root of 4 minus x squared. Since the tangent of theta is opposite over adjacent, the cotangent of theta is adjacent over opposite, which gives us that the cotangent of theta is the square root of 4 minus x squared all over x. And putting this all together, we get that the answer to our integral is negative square root of 4 minus x squared over x minus the arc sine of x over 2 plus a constant. And before we move on, let's just consider what if the problem instead had been the integral of the square root of 5 minus x squared all over x squared dx. I mean, in the 4 minus x squared, we felt very fortunate because our a squared minus x squared, the a squared part was very obvious that a was equal to 2. But it's just a matter of carefully canning the problems because you have enough work to do anyway with the trig substitution. This is the same problem, it's no harder. 5 is also a perfect square. It's the square root of 5 squared. And so you would start this problem by letting x equal the square root of 5 times the sine of theta, in which case dx would be the square root of 5 times the cosine of theta, d theta. And it's the exact same work from that point on. It's just that you're working with a slightly uglier number than 4 or 2, however you want to look at it. You're working with square root of 5, but same idea. Nothing conceptually different, just arithmetically different. Okay, let's try this one. The integral of 1 over the square root of 9 plus x squared dx. I'll get you started. This is of that second form, a squared plus x squared. And so start with let x equal 3 times the tangent of theta. If you start with let x equal 3 times the sine of theta, nothing good is going to happen and you're not going to get anywhere. So you have to start them right. So there were those 3 rules that I showed you at the beginning. This is of the form a squared plus x squared. And so you're using that second rule. We're starting with x is 3 times the tangent of theta. Again, we'll pause briefly after each part, but see what you can do. Go as far as you can. And if you get stuck, then hit play again and we'll catch up. All right, give it a try. Since x is 3 times the tangent of theta, dx is 3 times the secant squared theta d theta. That's enough to let us rewrite the original integral, all in terms of theta. I replaced the x under the radical with 3 tangent theta to get the square root of 9 plus 9 tangent squared theta there. And I replaced the dx with 3 secant squared theta d theta. In the denominator, I can factor out a 9. And I can pull the 3 secant squared theta up into the numerator. And 1 plus the tangent squared theta, this is a trigonometric identity that we've seen a few times recently. 1 plus the tangent squared theta is just the secant squared theta, which leaves us with a perfect square under the radical in the denominator. And after you do a little simplifying, you get the integral of the secant of theta d theta. And then you say to yourself, how do I do the integral of the secant of theta d theta? And the answer is you don't. I've given it to you. I give it to you on every quiz or exam. We did it in class together. And it's that the integral of the secant of theta is the natural log of the absolute value of the secant of theta plus the tangent of theta, plus a constant. And so this second step of how do you integrate the new integral that you come up with is actually a very easy one in this case, because if you might need it on your quiz or exam, I've given it to you. Don't forget that though. It'll be on the front of the exam with the instructions where people tend to read very quickly, if at all. And so remember to look for the fact that I will have given this to you if you might need it. And so all that's left is the third part of this problem, which is turning these expressions in terms of theta back into expressions in terms of x. For that, we make ourselves a right triangle. We label one of the non-right angles theta. We remind ourselves that x equals 3 times the tangent of theta, which is how we started. And so that means that x over 3 is the tangent of theta. And so opposite over adjacent is x over 3. And so we can label the opposite side x, the adjacent side 3. And the remaining side is the hypotenuse. We may as well call it c. And the Pythagorean theorem gives us that 3 squared plus x squared is equal to c squared. And so c is equal to the square root of 9 plus x squared. All that's left is to find the secant of theta and the tangent of theta. Well, we already know the tangent of theta. We have it right over here. It's x over 3. And so all that's really left is to find the secant of theta. And since the secant of theta is 1 over the cosine of theta, and the cosine is the adjacent over the hypotenuse, the secant is the hypotenuse over the adjacent. And the hypotenuse over the adjacent is square root of 9 plus x squared all over 3. We're finally ready to answer the problem. And we get that the answer is the natural log of the absolute value of square root of 9 plus x squared over 3 plus x over 3, all plus a constant. If you wanted to, you could combine those two fractions since they have the same denominator, but it's not necessary. Good enough as is. We've done plenty of work. Done. Just one more brief thing to say here before we move on. Suppose we had needed the cosine of theta instead of the secant of theta, so that that square root of 9 plus x squared was in the denominator. We had a 3 over square root of 9 plus x squared. I'm not a stickler for rationalizing the denominator in a situation like that. I am when it's a number. If you have something like 1 over the square root of 5, I want you to rewrite that as square root of 5 over 5. It's not hard to do. But for some expression like this, with some square root that's got variables in it and it's in the denominator at the end of a long, hard trig sub problem, nope, I'm okay with it. You can leave it in the denominator. So you don't have to. You can do the extra work and rationalize the denominator in that case if it makes you feel better. Don't make any mistakes. That's all I'll say about it for now. Let's move on and do one more. And of course, once again, when I say let's do one more, I mean let's you do one more. And of course, it's of that third form, because you may as well have one of each. This is of the form x squared minus a squared. And I'll start you off. Since we have something of the form x squared minus 4 squared, we start by letting x equal 4 times the secant of theta. If you start with x equal to 4 times the sine of theta or 4 times the tangent of theta, it's all over from the very first thing you wrote down and nothing else good will happen for the whole rest of the problem. Not that it won't still take you 20 minutes or a half an hour, it's just that you'll never get to probably any answer, and any answer that you do get to will be wrong. So make sure you start out right, like this in particular. So give this a try. And, pause the video, get as far as you can, and when you're ready, start it back up, and we will do it together. Since x is 4 times the secant of theta, dx is 4 times the secant of theta times the tangent of theta, d theta. And replacing all the x's with 4 times the secant of theta, and replacing the dx with 4 secant theta, tangent theta, d theta, you get this expression right here. You probably notice that the 4 secant theta in the numerator and the 4 secant theta in the denominator are going to cancel. So we'll do that in the same step as factoring out the 16 from underneath the radical. And we're left with this expression here. And again, all I've done is cancel the two 4 secant thetas, one in the numerator, one in the denominator, and factor a 16 out from under the radical. And then secant squared theta minus 1 is tangent squared theta. That's one of our trig identities. And I am happily left with a perfect square under the radical. So I can take the square root of that. And when the smoke clears, you're left with 4 times the integral of the tangent squared theta d theta. Next step, to integrate that. It's very similar to one that we did earlier in this video. We did something with the cotangent squared theta. We do this one the same way. We use a trig identity to rewrite tangent squared theta. And tangent squared theta is equal to secant squared theta minus 1, and that you can integrate directly. The integral of the secant squared theta is the tangent of theta. The integral of 1 with respect to theta is theta. You have to be a little bit careful that the 4 is times the whole thing, or is multiplied by the entire thing. And so we may as well distribute that and rewrite it as 4 times the tangent of theta minus 4 theta plus a constant. All that's left is to turn those thetas back into x's. From the very beginning, we have that x is equal to 4 times the secant of theta. And so x over 4 is the secant of theta, and that immediately tells us that theta is the arcsecant of x over 4. All that's left is to find the tangent of theta, and for that we use a right triangle. I should probably also mention that you could also use trig identities to do it. I like the right triangle way. It's sort of more straightforward and a little bit more obvious what's going on. If x over 4 is the secant of theta, well, the secant of theta is 1 over the cosine of theta, and the cosine of theta is the adjacent over the hypotenuse. And so the secant of theta is the hypotenuse over the adjacent, and so we have that the hypotenuse is x, and the adjacent side is 4. We'll label the unknown side b, and by the Pythagorean theorem, 4 squared plus b squared is equal to x squared. We can solve that for b. To get that b is the square root of x squared minus 16, which should give you a good feeling. Look, there's a square root of x squared minus 16 in the integral that we started with, and so that the answer should have something to do with the square root of x squared minus 16 seems reasonable and appropriate. Okay, using this information to find the tangent of theta is the opposite over the adjacent, which gives us that tangent of theta is square root of x squared minus 16 all over 4. We're ready to write down the answer. And I've switched colors so that the answer doesn't get lost in all this work here, but basically I'm taking this expression here, which was our expression for the answer, and rewriting it in terms of the things that we just learned. And after you simplify, you get that the original integral is equal to the square root of x squared minus 16 minus 4 arcsecant of x over 4 plus a constant. That's trig substitution. As I mentioned before, no part of it is particularly hard, but then again, no part of it is particularly easy either. And there are lots of parts. Don't rush. No one ever did a trig substitution problem quickly. It can't be done. So expect to spend some time. Do them slowly and carefully. Make a mistake right at the beginning and you'll pay for it for the rest of the problem. If you're going to make a mistake, try to make it at the end, but even better, don't make a mistake. So practice some of these, and we'll do some in class if you like. Have fun, and I'll see you soon.